The profound implications of neuroengineering are explored, delving into how human intellect can be seamlessly integrated with artificial constructs. A fascinating journey into the convergence of neuroscience and engineering awaits, unveiling the transformative potential of this rapidly evolving field. Imagine a future where your thoughts aren't confined to your brain, where intellect can be uploaded, shared, and even enhanced by machines. Is this the ultimate evolution of humanity, or a terrifying step into the unknown? Join us as we explore the mind-bending reality of neuroengineering and what it means for our very existence. What if the next leap in human evolution isn't biological, but technological? Forget VR headsets, we're talking about direct brain-to-machine interfaces. Discover the groundbreaking work in neuroengineering that's poised to merge our minds with artificial intelligence, unlocking potentials we've only dreamed of. This isn't science fiction anymore. Are you ready for a world where disabilities are a thing of the past and human potential knows no bounds? Neuroengineering is rapidly making that a reality. We're talking about restoring sight, enabling thought-controlled prosthetics, and even enhancing cognitive abilities. Prepare to be amazed by the transformative power of bridging brains and machines. Neurology, particularly the study of brain-computer interfaces, BCIs, is bridging the gap between the human brain and machines by allowing direct communication and control. BCIs convert brain signals into commands for external devices, offering revolutionary benefits for individuals with motor or communication impairments. This technology allows for interaction with computers, robotic limbs, and other assistive devices, bypassing damaged neural pathways. Sophisticated algorithms and AI analyze these signals to decipher the user's intent, translating them into commands for the connected device. The translated signals then control external devices, such as robotic limbs, cursors on a screen, or communication interfaces. They come with risks and ethical considerations. Non-invasive BCIs, like EEG, are safer but can be less accurate. Decoding complex brain signals and ensuring reliable control remains a challenge. Brain-computer interfaces, BCIs, are enabling paralyzed individuals to communicate and move again by translating brain signals into commands for external devices. These signals, captured by electrodes either implanted or on the scalp, are interpreted by the BCI and then used to control computers, robotic limbs, or other assistive technologies. Recent research suggests that hybrid BCIs may improve overall BCI performance through combing different features of brain signals, which can include the use of two BCI navigational paradigms, for example, SSVEP and imagined movement, or through integrating BCI and another system, for example, an eye tracker. Brain-computer interfaces, or BCI for short, use changes in the electric activity of the brain to control a device, like a computer, or a game, directly just by changing your thoughts or attention. While direct brain-to-brain communication using machines is a fascinating area of research, some fundamental limitations make achieving seamless, telepathic-like communication with machines currently impossible. Specifically, the complexity of the brain, the lack of a complete understanding of how thoughts and emotions translate into electrical signals, and the difficulty of creating bidirectional, high-fidelity interfaces all pose significant hurdles. The human brain is incredibly complex, with billions of neurons and trillions of connections. Even with advanced brain-computer interfaces, BCIs, researchers are still in the early stages of understanding how thoughts, emotions, and intentions are encoded as neural activity. Current BCIs primarily focus on decoding basic motor commands or simple cognitive tasks. The complexity of higher-level thought processes, like abstract ideas, emotional nuances, and subjective experiences, is far beyond our current ability to decode and transmit. Addressing the fear surrounding AI's potential impact on control and autonomy requires separating hype from reality by understanding the difference between narrow AI and hypothetical superintelligence, recognizing the importance of control in human well-being, and acknowledging both the potential benefits and risks of AI advancements. Instead of dwelling on hypothetical scenarios, it's crucial to focus on the practical applications of AI in our daily lives and how they can be used to augment human capabilities and improve efficiency. Generative AI, which is capable of creating new content based on existing inputs, is a significant area of development. While powerful, it also relies on human input and control, and it's important to understand how these systems learn and generate outputs to alleviate concerns about unintended consequences. To enhance privacy and security in your digital life, focus on securing your devices, managing your data, and being mindful of your online actions. This includes using strong passwords, enabling two-factor authentication, encrypting your data, and being cautious about the information you share online. Enable 2FA on all accounts that support it for an extra layer of security. This adds a second verification step beyond just a password. Encrypting your hard drive and sensitive files helps protect your data if your device is lost or stolen. Regularly update your operating system, apps, and antivirus software to patch security vulnerabilities. Be mindful of the information you share online. Avoid oversharing on social media and be cautious about providing optional information. Regularly search for your name online to see what information is publicly available and take steps to remove sensitive information. The Human Connectome Project, HCP, is a large-scale effort to map the structural and functional connections within the human brain, aiming to understand how these connections relate to behavior, cognition, and disease. This ambitious project utilizes advanced neuroimaging techniques like diffusion MRI and functional MRI to create a comprehensive connectome, or a map of the brain's connections. The ultimate goal is to unlock deeper neural secrets and potentially revolutionize our understanding of the human brain. The HCP focuses on mapping the macroscopic connectome, which involves connections between areas of the brain at a resolution of about 1 cubic millimeter or greater. This is distinct from the microscopic connectome, which aims to map connections between individual neurons and synapses, a task currently limited to smaller brain regions in animal models. Neuronavigation system is a technology used primarily in brain and spinal surgeries. It functions like a GPS system, providing surgeons with precise guidance around complex anatomical structures, facilitating their navigation with high accuracy. Neuronavigation is possible and widely used in modern neurosurgery. It's a technology that utilizes medical imaging, computer software, and tracking devices to assist surgeons in precisely navigating and operating within the brain and spine. Neuronavigation is essentially a GPS system for the brain and spine, guiding surgeons with real-time 3D imaging and tracking during procedures. It helps surgeons visualize the surgical area in detail, plan the approach, and accurately target tumors, lesions, or other abnormalities while minimizing damage to surrounding healthy tissue. To stay informed and participate in the field of digital transformation, actively seek out information through industry publications, online communities, and events. Engage with experts, attend workshops, and experiment with new technologies to deepen your understanding and develop practical skills. Furthermore, participate in discussions, share your insights, and collaborate with others to contribute to the ongoing evolution of this transformative field. The future is not about humans versus AI, it is about humans and AI working together. The most successful industries will be those that leverage AI's computational power while utilizing human intelligence to make informed, ethical, and creative decisions. Widespread neurotech, encompassing brain-computer interfaces, BCIs, and neuromodulation, is poised to bring about significant societal transformations. These technologies offer potential benefits like improved treatments for neurological disorders and enhanced cognitive abilities, but also raise concerns about ethical implications, social equity, and the very definition of what it means to be human. Neurotech can revolutionize healthcare by enabling more precise diagnoses and personalized treatments for a wide range of neurological and mental health conditions. BCIs, for example, can restore movement in paralyzed individuals, while neuromodulation techniques like deep brain stimulation can alleviate symptoms of Parkinson's disease and depression.